Welcome. In this lecture, we're going to go through approximating the area under a curve using right endpoints. We were using left endpoints before. These are the endpoints of the interval. We were using left endpoints before. Now we're going to use right endpoints. So here's our task. So our task is going to be, we want the area under the curve. First, we'll do it with a specific example, and then we'll move to something general. So under the curve, f of x equals, and we're going to do x squared plus 1, and we're going to go on the interval. So on the interval, where we have, minus 1 to 1.5. And we're going to want to have, so this is going to be with 5 subintervals. So 5 subintervals with 5 subintervals. Sometimes one just says intervals here. Some intervals helps to kind of, they're like little intervals sitting inside the big interval. Okay, so here's our picture. So, oops, I want this to be orange. I want it to be orange, and I want it to be a fresh orange so that you can see it really nicely. Okay, so this is our x, and we have our curve, right? We have our curve. Well, we want our y. That was what I meant to use this for. So we have our y. So that's our y, and then we have our curve, right? We take y equals that, so that's our curve. And again, I'm making it a little more flat than maybe realistic, but it makes the picture easier. I'm also making it less symmetric than it ought to be, but that's okay. So this is the curve y equals x squared plus 1, just like over there. And then we know how to do the width, right? Because we've done that several times now. So could right be, well, first off, let's put on our endpoints. So we have minus 1, and then we have 1.5. Okay, and then if we want the width of each of these subintervals, right, we need that so we can kind of figure out where everything goes. So we know that our width, and our width we call delta x, right, that this is going to equal, right, we need our entire length. So we take 1.5 minus 1, and then we divide it by the number of subintervals, which is 5. And we get 0.5, so this is going to equal 0.5. Great. So that's going to kind of indicate to me that we have, so these are, so this would be like minus 0.5, this would be 0. Right, I'm just adding my width each time, so I'm adding 0.5, so I get minus 0.5, I get 0, I get 0.5, and then I get 1, and then I go up to 1.5. Okay, and then we know that these areas that we're looking at, we're going to get by going, well, now, and we were going up and over, now we're going up and over, right? We're looking at the right endpoints. So the right endpoint of this interval is minus 0.5, so I go up and then over and down. For this one, the right endpoint is 0, so I go up and over and down. The right endpoint of this interval is 0.5. I take it, right, I go like that. For this subinterval, it's 1, so I go up. And for this one, it's 1.5. Okay. And then these are the areas that we look at. So this is area 1. This is area 2. This is area 3. This is area 4. And this is area 5. Right, so this area that we're approximating is going to be the sum of these. So, right, we're using these rectangles to approximate the area under the curve. So we need to take the sum of their areas. So I want the area of A1 plus the area of A2 plus the area A3, A4, and A5. Okay. And then we kind of remember this width is delta x, right? For each of these, this width, I'll write down here, so this width is delta x, right? And then the height now, though, this is kind of one of the key points of what's going on. So now my height is going to come from minus 0.5 f of minus 0.5, right? Because the height is happening on the right-hand side, okay? And again, I feel like this is hard to see. For some reason, none of the greens I want to use today are up to snuff. They might be hard to see. There we go. Hopefully that's visible now. And then, so we're going to go all the way up. And on this side, right, this is where you can see it the best. So this point here is going to be, the point is going to be, well, I take 1.5 and then I stick that in, right, to my function f of 1.5, right? And this is actually, make this big here, and this is actually this height here is this f of 1.5. Okay, so this height here is actually f of 1.5. Okay, so that gives me the next part of this, which is that I can go through and I have, so this is going to be my width times my height, which in this circumstance is f of 0.5, so f of 0.5, and then I need to add, so then I have my delta x again, and now I've got to do it for f of 0 for this height here. Oops, that should be a delta x. Delta x. And then I have my f of 0. That's really difficult to see. It's worth reaching over and getting something to clean that. So I have delta x times f of 0 plus delta x times f of 0.5. Oh, this should be a minus 0.5. Did I write 0.5? I wanted minus 0.5 there. And then this should be f of 0.5. And then I, right, because I'm looking at this rectangle. So I'm looking at this height, which is the f of 0.5, and then this one's going to be f of 1. So delta x times f of 1. So I have plus, and then I have delta x times f of 1. And then I have 1 left, right? Looking at this area, so this height, I've already told you, is f of 1.5, and that again is delta x. So I have delta x. Why don't you write that each of these is delta x? I think that kind of fits there, and then you can kind of see what we're doing here. A little bit better, because I know these are confusing. The more clear we can be, the better, because these are historically one of the most intimidating aspects of calculus. Okay, 1.5. Great. So then we just kind of compute whatever these f values are by sticking them into the function, right? And we likely pull out our delta x, because that's kind of a lot to have it in each term, but we can use our distributive property nicely here. So we pull out our delta x, which we know is 0.5, so from over there. So we have 0.5, and then we're going to multiply it by each of these. So let's go ahead and do that. So f of minus 0.5, so we should get 5/4 plus, and then we should get 1 plus 5/4 again from this here. And now we need to do this one, and that should be 2. And then we need to do this one, and that should be 13/4. And so altogether, what we're going to get as an answer is going to be 35/8. Okay. But you can kind of see, again, we're just adding up the areas of these rectangles. Our width is our delta x, which you compute over there. Our height comes from the y value, which is actually sticking our right endpoints into the functions. Okay. And then this is where, and I know that this gets a little bit tricky, but here's kind of the formula. So the more generally, so what is our more general formula? So more generally, we're going to have that if I have R n, well, this is going to equal, it's going to look a lot like this. We just have to put in our x j's, remembering that actually in this circumstance, right, and let's kind of write these in, so maybe that'll help a little bit here. This is actually x0, x1, x2, x3, x4, and x5. So you can see, instead of starting with x0, we actually start with x1, and we go all the way, because we're looking at the right endpoints. The right endpoint of the first interval, right, is at x1. The right endpoint of the second interval is at x2. The right endpoint of the third interval is at x3. The right endpoint of the nth interval is at xn. Okay, so the formula is going to actually look a little bit different this time. So this is actually going to equal, right, where we multiply in each circumstance, we take our delta x and we multiply it by our f of, and this time we actually start with x1, right? And then we do this, we keep doing this, we go all the way up to, we do our delta x, and then we go f of xn, and this is the the nth interval, the right endpoint is actually, so if this is a fifth, it's 5, so it's actually the nth. All right, we do xj, sorry, xn, so this is an xn, okay? And in sigma notation, so this is the formula here, so this is our final general formula. Okay, and then how do we write that in sigma notation? So like this, right? And so in sigma notation, kind of as we did with the left, we want to do sigma notation. And for that, right, we're going to take, so we have that R n is going to equal, and now notice that we go from 1 to n, so we don't need to go xj minus 1, we can just do xj, right? So we can go the sum from j equals 1 up to n of, and then we have this, this delta x times f of xj. Okay, and so this is just the other notation for the same thing, right? With the big difference being, and it's good to notice differences. I tell students to kind of stare at that for a moment to see the differences. And what you're going to see there is that actually the only thing that's really different is that we have xj instead of xj minus 1, and that's because everything's kind of shifted over. When we're looking at the right endpoints, we start with 1 and we actually go up to n, right? We go up to xn. Okay, so this is like when we're doing our heights, right? Because we do our heights on the right. Okay, so I hope that made some sense, and I will see you in the next lecture.